So let's just say we've got this dude with glasses and a cool gray baseball cap, and let's pretend that he is riding an elevator. So he's standing on a scale where the floor of the elevator is this black floor, and the red line represents some sort of a bathroom scale or something that can measure the force that the floor is pushing up on him with. And that's essentially what scales do. They measure the normal force, usually via a calibrated spring. Okay, this is Physics Farm, and this is the elevator problem. Okay, let's take a look at this problem in detail. We always start a dynamics problem, a problem dealing with forces, with a free body diagram. It's a simplified sketch. A box usually will suffice. You don't need to make sketches or pictures or anything like that. And you draw the forces acting on the body. In this case, let's assume that the guy is not accelerating. He's just sitting there at rest in the elevator. There's a couple of forces that you should be familiar with. The first one is the force of weight, or the force of gravity, or mg. All of these are going to be directed straight down towards the center of the earth. There's also the floor pushing back up on the guy. In this case, that's the force that the scale reads. We also call that the normal force. You could call that the force of the scale in this particular application as well. All right, so in this particular case, let's and in all free body diagrams, it's important to agree on a convention for a coordinate system. Let's call up positive and down negative. You can choose other conventions. As long as you kind of stick with it throughout the problem, you'll be just fine. So I always start by asking myself the question, is the sum of the forces equal to 0 acting on the body? In this case, the answer is going to be yes, because he's not accelerated. Newton's second law says that if there is a net force on an object, it will be accelerated. The first law says that if the sum of the forces is 0, it'll remain at rest, or it'll continue moving in a straight line if it's already moving. I've written the equation out. Notice that the normal force is positive, the weight force, or the force due to gravity directed downward in purple, is negative. So I've made sure to include that vector direction, and they're equal to the net force. So I can write it more succinctly as the normal force minus the weight is equal to ma. I've substituted ma in for F net. That's Newton's second law. Let's keep in mind here that the net force is 0 because he's non-accelerated, and therefore I could simply write it as the normal force minus the weight is equal to 0, or for simplicity, the normal force is equal to the weight. Their magnitudes are equal, their directions are opposite. Okay, that is the elevator problem, in its most basic form, where you're not accelerating. But the problem becomes a little bit more sophisticated if the elevator is accelerating. Notice that if it's moving at a constant velocity, you would really have similar, an exact free body diagram as we had in the previous one. So now the elevator is accelerating, so let's go ahead and assume that the direction of acceleration initially is up. So again, we always start with a free body diagram. We have a weight force going downwards. Notice that we have a normal force going up, but now because he's accelerating, that normal force is actually larger and produces a leftover force, a resultant force from the sum of the normal force and the weight. If I were to describe that numerically using algebraic equations, I would simply look at that free body diagram and write the equation representing what I've sketched in the free body diagram. I always start by asking myself if the sum of the forces equal to 0. In this case, no. There's a leftover force which is producing the acceleration. So now I can write my equation as the normal force plus the weight, which is negative, is equal to the net force. Notice that that looks very similar to what we had previously, except now the net force is not going to be 0 because there is a non-zero value for acceleration. Okay, so let's go ahead and so we've got the normal force minus the weight is equal to ma, and now we can rewrite that. I've simply substituted in mg in for the weight force, so I've got normal force minus mg is equal to ma. Notice that the normal force is often what I'm solving for if I'm being asked what the scale would read, in this case if the man were being accelerated upwards. So I'm going to solve this equation for the normal force. I get ma minus mg, I can factor out an m, so the normal force is equal to mass times the difference between his acceleration and the acceleration due to gravity on Earth, small g. All right, let's take a look at this equation. We've substituted 9.8 meters per second in for g, and you should be focusing on this value of a now that we have this expression at the bottom of the page. If the acceleration is 0, then the normal force would be equal to mg, or m times 9.8, which makes sense. If the acceleration is positive, meaning that he's going upwards, I'm going to get some value for the normal force that's potentially larger than it would be if a were 0. It is larger than if it were a were equal to 0. And if the acceleration is negative, then the normal force in the scalar reading would be smaller than you would expect. And this is consistent with your physical experience. As you've been in an elevator and it accelerates upwards, you feel that the force is pushing on you more. Your knees tend to feel that stress. And then conversely, when the elevator is accelerating downward, you feel a little bit light. And that's because the value of the normal force, the force that with which the floor pushes up on you, has gotten smaller.